Hello, mates. Yeah, I know my quality is bad, but I'm hoping some people are following this as a course. Are following this as a course. And if you remember, if we're following this as a course, we've just finished gravitation, so I ticked it. But on Doppler effect, I also added stars because the Doppler effect that we will learn, we are going to apply it to stars. So I just added in the stars. So I hope that doesn't confuse anyone. So now let's start the Doppler effect. I've already written a slide. This slide, this slide is for Doppler effect because that's what we are starting now. Now imagine there is a police car racing down the road, and you're standing here, you're the observer. When the car gets closer to you, as the car is approaching you, you pick up a noticeable change in the sound. You pick up a change in the sound of the siren or the sound of the car, or even imagine a motorbike rushing past you, or just racing past you rather. You will hear the sound change as it passes you and as it goes away. It is because of the effect called the Doppler effect. When it is approaching you, the sound waves or the waves, they become shortened because as you can see, this car is approaching from the left hand side and it's approaching in this direction. When it's approaching in this direction, and the propagation of the waves, they are in this direction as well, so they are both in the same direction. The approach of the of the object and the propagation of the waves. So by the Doppler effect, the wavelengths decrease as they get to you. The wavelengths decrease as they get squashed as they get to you, like this. And when it's receding, this object is moving in this direction, and the propagation of the wave is in that direction towards you. It's coming towards you. So they are in opposite direction. So the waves, they become stretched out. This I can say it is due to greater distance. It is due to greater distance and a fixed velocity of travel of these waves. It's a fixed velocity of travel of the waves. You know, the sound waves and sound waves, they have a fixed velocity of travel. Let's just say fixed. To get rid of all the other assumptions, they have a fixed velocity of travel, but as the distance is increasing, these waves, they get stretched out. They get stretched out so that they can reach you with a finite speed that is fixed. So yeah, the waves get stretched out as the car is receding. So those two phenomena result in what? In different sounds as it passes you and then as it goes away. But now we're not going to be talking about sound. We're going to talk about light, but the principles are the same. Imagine this is light. Imagine this was light. And we are going to discuss light using the electromagnetic spectrum. When it is approaching like this, the wavelengths get shortened. The wavelengths get shortened, isn't it? And when it's going away, the wavelengths get longer. So now imagine we have our electromagnetic spectrum. If we have our electromagnetic spectrum, actually maybe I should have written it the other way, but these are short wavelengths and these are long wavelengths. This is the long side, this is the short side. So now imagine the color that we are observing is somewhere between yellow and green. Imagine this is the wavelength that we know. What I basically mean is, imagine this color, this light source, the light source of this car. Imagine we knew what wavelength it emits when it's just resting like this. We take that light source and then we measure the wavelength. When it's not moving, we just measure the wavelength. Imagine this is the wavelength that we get from this bulb. Yeah, if this is the wavelength that we get, and then we put it on top of a car and let it move, as it is moving, it will experience what? The Doppler effect. If it's approaching us, its wavelength, when it gets to us, it appears shortened like this. The wavelengths appear shortened when it gets to us. and when it's receding away, the wavelengths appear elongated. So this is the Doppler effect on light. So let's see what happens to our what happens to our electromagnetic spectrum. Now, when it is approaching, we are experiencing what? Shorter wavelengths. We are seeing shorter wavelengths, but we'll be like, but this thing had what? Had a color in this region originally when it was just standing there. When we just put it there, it had what? It had a color in this range. But look at it, its wavelength is not this wavelength anymore because it's being shortened. You see, so it's being shortened, which means I'm now observing probably maybe a wavelength that is now at this, that has been shortened. That's the wavelength that I'm now observing. It is what? Approaching. So I'm going to call it the wavelength of approach. That's the wavelength of approach that I'm now observing. And I'll be, what color will I be seeing now? I'm no longer seeing this color because this was the resting color. But as it is moving towards me, I'm not seeing this color. And it looks a bit bluish because it's closer to blue. It looks a bit bluish. So that is the important part about what? About the Doppler effect on light. On approach, color appears blue. Okay, on approach, let me write. On approach, we have shorter wavelengths. On approach, we have shorter wavelengths, and the color appears blue. But this phenomenon was given a special name. It's called the blue shift. Because now the wavelengths are moving from where they were originally towards the blue end. They're moving towards the blue side. So the color appears blue. So it's called what? The blue shift. So on approach, we have shorter wavelengths, and we also have the what is called the blue shift. So now on receding, this is what? This is the situation. Receding, it's going away. We are experiencing longer wavelengths. So on receding, we have what? We have longer wavelengths. And what longer wavelengths? What does that mean now on our electromagnetic spectrum? It means we are now experiencing maybe a color that is like this, the wavelength that is like that. So I'm going to call that lambda r, which is lambda for recession, when it's receding. So this lambda for receding, can you see it's now moving towards the red end of the spectrum? So now the color that I'll be observing is not the natural color. I'm now observing this color that is reddish. So color appears red. The color appears red. Therefore, it was given a special name called what? A red shift, because it has shifted towards what? The red side. So when an object that is emitting light approaches you, you experience a blue shift. You see the color tend to blue. This may not be noticeable when we're dealing with our normal police cars and all of those, but when we're talking about stars and using those telescopes that are very sensitive instruments, you actually see that blue shift is let's say if you draw a star closer as it is approaching, it becomes its wavelength, its light becomes blue shifted. But if it's moving away from you, you see a red shift. We are going to see that when you're doing the calculations for stars. So this is what? This is the Doppler effect, the blue shift and the red shift. Blue shift being on approach and red shift being when the car is moving away, or in other words, when it's receding. Let's just take a quick example to see something that I need to show you now. Doppler then went on to do various experiments. We did various experiments to come up with at least a formula that allows someone to calculate these wavelengths, because these wavelengths, lambda r and lambda a, someone needed to know them. So that you know, is it coming towards me? Is it going far? You can know them from what? From experiment. But you might need to know how fast is it coming towards me after you measure this from experiment. Because let's say you have a meter here, a very sensitive instrument here. If you have a very sensitive instrument there, you can measure, oh, this wavelength is this. this wavelength on approach is this, then you now have this wavelength of approach. But you can ask yourself a question. So how fast is this thing approaching me then? Because you know that the speed of this thing is going to affect the what, the wavelengths here. If it's moving slow, you will not see as much red shift. But if it's moving very fast, you see great red shift. Same applies for this side. This stretching out of the waves depend on the speed of the object. So you may measure it. You may measure both of these, but you need a way to compare it to this resting wavelength for you to calculate the speed of what? Speed of approach. So that's what Doppler went on to do, to come up with the formula that calculates that speed. His formula says V over C, which is C being the what? The speed of light. So velocity, this velocity is either velocity of approach or velocity of going away, depending on whether it's what is receding or approaching, is equal to lambda, the observed lambda, or the one that you have measured with your instrument, minus lambda that is found in the lab, or the resting lambda of the light source, the resting lambda of the light source, all divided by lambda of the resting lambda, or the lambda from what, from the lab. So this lambda from the lab, you already know. You can Google anything, any light or whatever. This you already know because you've measured it in the what, in the lab. You can take your bulb and then place it there, and then take your meter that you use to measure, or whatever instrument you are using to measure the lambda wavelength when it's just sitting there. And then this observed is the one that you're going to see as the object is moving. So this is either lambda A of approach, or lambda B that you're going to see when it's what, lambda R, I mean, when it's receding. So it's either lambda A or lambda R. So let's get an example. Consider when lambda O is equal to 6001 angstroms. These are called angstroms. Angstrom. Yeah, I think it's angstroms or angstrongs. I'm not quite sure, but I just know it's angstrom. It's either angstrongs or astrom. I'll confirm that and I'll put that as a description. So yeah, and then consider lambda L, the resting wavelength, to be 6000 angstrom, like this. The waves that we are dealing with are light waves. Light waves, it's difficult for you to measure in what? In meters, because when you want to measure the wavelength of in meter, you might come up with 6 times 10 to the power of minus 9 meters. This is not very useful. This is not quite useful when you're dealing with such things, because you are going to have these -9 and stuff. It just becomes cumbersome. It becomes just too many calculations. So we use the unit, the angstrom unit. That's the unit that we use when we're doing these calculations. So since we have observed this object was moving already. We have observed this. So we want to know, was this object coming towards us, or was it going away, and at what velocity? That's what we need to know. So we need to calculate V. C is a constant that we know already. This lambda O is the one that we're given. Lambda L is this one. So let's calculate V. V is equal to lambda O minus lambda L all over lambda L times C. That's what we know, right? If we know that, then let's put in the figures. This will be equal to 6001 minus 6000 all over 6000 multiplied by this one is 3 times 10 to the power of 8 meters per second. I can assume it to be that 3 times 8. I can assume it to be 3 times 8 to the power of 3 times 10 to the power of 8 meters per second. When you calculate this, you are going to get 50,000 meters per second, which is basically equal to 50 kilometers per second. So this object is moving very extremely fast. It's moving extremely fast. It's moving at 50 kilometers per second. But now, by convention, by convention, positive speed basically means what? Means recession. Means this thing is what? Is receding. So it's receding away from us at 50 kilometers per second. So I'm here, there you are, or there I am, and then this, so it means that the police are receding away from us at what? They are receding away from us at 50 kilometers per hour. It also makes sense that it's receding, because can you see the observed lambda? The observed lambda here is greater than the what? Is greater than the receding, and we know that when the lambda increases, when it's longer, it becomes a what? A redshift, and redshifts okay, and what? On recession. So here you could have already concluded that this thing is what? Is receding, because the lambda that has been observed is greater than the lambda at what? At rest. So it moved towards the what? The redshift of our spectrum. So these are the basics of what? Of Doppler effect. I hope this video I've explained properly what Doppler effect is, and I've just shown you an example of just calculations. In the next video, we are now going to get into stars to see how to apply these to stars. So stay tuned for that one.